Good afternoon, everybody. I'm Prashant. I'm a PhD student at Dartmouth, and I work with Sergey and Sean. And this work was from my internship over the summer at SRI with Michael, Gabriella, and Ulf. Ulf is here today. Okay. So this work was funded by SRI International's uh, independent R&D initiative. So this is the outline of my talk. I'm going to give you an introduction of the LangSec viewpoint and an overview of IoT protocols. And I'm going to discuss parsing errors and protocol state machines in IoT protocols. And then I'm going to go about describing our approach to tackling this problem and the results of our work. Okay, so what's the real problem over here? So problem we are trying to deal with. So how do IoT protocols actually differentiate between good input and bad input, and how good do parser combinators actually perform in constrained devices that use these IoT protocols, and how can we actually build these parsers well? Um, so this is what LangSec is all about, I would say. Uh, so differentiating between a set of possible inputs and actually identifying the input that is expected by our system is what we are trying to deal with over here. So validating input is judging what effect the code, the input is supposed to have on the code. Uh, so the recognizer design pattern is the design pattern where we actually take the grammar of the language and then build a recognizer for the language, which rejects all the messages that do not conform to our language, and then process and accept only objects that are well typed and no raw input actually. Okay, so for our work, we dealt with two industrial IoT protocols. One is called MQTT, which happens to be a publish-subscribe protocol, and it's widely used in pipelines and the oil and gas industry. And the other protocol that we were dealing with is the XMPP protocol, which is being used widely in industrial automation, and it happens to be XML-based. Okay, so first the MQTT protocol. The MQTT protocol is actually really lightweight, and it has only a fixed set of messages. And when you publish a message on a particular channel, there are no real details about who the sender is. And so the MQTT protocol has a really fun option, which is you can subscribe to the hash symbol, and then that would basically give you messages from all the channels on the particular server. It's a very, very, very bad idea, but I'm guessing that administrators find it pretty handy. Okay, and one thing about the MQTT protocol is this, that as per the spec, TLS is optional and it's not enforced by most servers and most providers. So the packet format for MQTT is very simple, and both the protocols that we are dealing with are application layer protocols. And so the MQTT protocol basically has a 1-byte header with a message type and quality of service, 2 bits for quality of service. And so there's a remaining length field, which happens to be at most 4 bytes. And then there's the payload, which is not really fixed size. And so the protocol state machine for MQTT is again fairly simple because the number of messages are very limited. So the client sends a connect message, and then the server responds, and the connection is completed, and then the client keeps sending ping messages to the server to keep the connection awake, and then the client can also subscribe to a particular channel, and then the server will send an ACK. That's about it. It's a very simple and straightforward protocol. The second protocol that we were dealing with is the XMPP protocol, and as I said earlier, this happens to be XML based, and almost all providers of XMPP now enforce TLS version 2, and most of the servers available right now do not really give an option to disable it. And there are other options like authentication, which is still optional. And in our implementation, we actually made a design decision to enforce it in our architecture. Okay. So this is how a simple XMPP protocol messages look like. So there's a message tag with an ID and type and to and from. And the active tag is basically to keep to basically denote that the client that is it's basically the state of the client. So there's an active, inactive, busy, those sort of states. And the success message is the message that is sent by the server when you send a TLS request. And it's a TLS request, which is a proceed message, and then it comes back with the success. So the XMPP protocol state machine is slightly more complicated. So there are way more states because like the stream message is actually sent 3 times. So one in the initial stage where the connection is being initiated, and then when the TLS connection is being initiated, and then when the authentication happens, and then when the binding happens. So the stream message is actually sent time and again, and each stream message actually has fields that are unique to that particular message. Okay, so our contributions basically over here was this, that we use the Hammer Ruby bindings to build these parsers, and then we basically demonstrate that to build these parsers in an IoT setting, it's not really all that much effort as we would think. These parsers are not really that difficult to write, and in terms of human effort in the number of lines of code that it took, it was very, very, very minimal. And we actually built fully functioning implementations with a lot of options and a lot of features. And even then, it was not really all that much of an overhead in terms of CPU time, nor the lines of code that it took us. Okay, so parsing in the IoT is also a very serious problem, like everywhere else. And we studied the CVE lists for the 2 protocols that we are talking about. And we found that several of the popular implementations industrially available have been exploited by crafted packet bugs. Not so much for the MQTT protocol, because although it is widely used, it seems to be very sparsely reported on the CVE lists, whereas XMPP seems to have way more vulnerabilities than crypto vulnerabilities actually. Okay, so this is basically an interesting bug that we found on, that we didn't find, but we found on the CVE list. It was the IBM Insight MQTT bug, where in the authentication message, the MQTT client sends a particular crafted packet, and then the server is forced to restart. Okay, so our approach over here was basically using parser combinators to build our individual parsers for each state. And we used the Ruby bindings, as I said. We also made use of a Ruby gem called the state machine gem to implement our protocol state machine. So our methodology was this, that we read through the specifications for these protocols, and we extracted the protocol state machine, and we enforced some rules that we thought were essential, like authentication, TLS, and those sort of rules that we thought were actually essential. And then we built the state machine using the state machine gem. And then for each of the particular states, we defined a separate parser. So there is a separate parser for each of the states in the protocol state machine. So we made use of the state machine gem, as I said, and this is the syntax of the state machine gem, where you can clearly specify before transitions and after transitions. There are the state machine gem has a very robust way of doing callbacks, and you can set events and states. Like the transition helper method basically denotes that when a particular event happens, then you can basically transition from one state to another state. And the state machine gem also has a very robust set of helper methods to write tests. Our next step after extracting the protocol state machine was actually writing individual parsers for each of the receiving states. And for this purpose, we first we extracted the grammar and wrote it down, and then we converted that to a parser combinator. So the best thing about Hammer is this, that when we actually started writing it, we realized that the code actually looks exactly like the grammar that we put down. And and it was very easy to translate our grammar into the code specification over here. So the limitations of our work that we feel, could be overcome, but I don't know at what time frame. It was this, that it's a very tedious process of actually going through hundreds of pages of protocol specification and actually extracting the protocol state machine and the grammar. So a lot of the protocols that we were looking at did not even have a clear state machine diagram. So then we actually had to read through a lot of it and actually extract it. And there is also an overhead to recognizing every message. So we actually performed our experiments on a Raspberry Pi, and we found that for the XMPP protocol, it was in the order of milliseconds, and for the MQTT protocol, it was in the order of microseconds, actually. So there is a small overhead to recognizing each message fully, but we feel that it is a price we should be willing to pay. Okay, so our results. So we made use of a bunch of techniques to validate our work, and the first one was that we performed timing analysis and on each of our parsers that we wrote, and we wrote unit tests while writing the code, and we also tested our code on using a sample set of messages that were that we took from the CVE list, basically messages that are known to be have been known to be malicious in the past, and we ran our parser on those set of inputs, and saw our parser actually reject a lot of those messages. Actually, all of those messages, not a lot. So performance-wise, our implementation actually took lesser time to establish a connection when it came to the MQTT protocol, and it took slightly more time than a few implementations of the XMPP protocol based on different languages. And so yeah, we were using a Raspberry Pi to run our tests, and we used the Wines XMPP server and the Mosquito MQTT server to perform our experiments. So our implementation actually had a bunch of receiving states, like the stream 1, proceed, stream 2, and so on. So the number of lines that it took us in Hammer was very minimal, like less than 40 actually for each of the messages. And as you can see, even the CPU time is quite reasonable for XMPP messages. And we followed the exact same approach for the MQTT protocol, where we wrote parsers for individual receive states, and we again saw that the CPU time for each of these messages was very minimal, and the number of lines of code was way lesser because the MQTT protocol is significantly simpler in comparison to the XMPP protocol. Okay, as I mentioned earlier, we wrote unit tests for almost each of our parser, and we also wrote unit tests for the protocol state machine, and we saw that we actually covered 100% of both the protocol state machines for XMPP and MQTT. And in terms of parser validation, we were slightly behind, but I would think that it's still pretty good. Okay, then what we did was that we started building a simple fuzzer that would basically generate messages taking our parser combinator object as an input. So since we did it in Ruby, it was a really interesting task for us. I think the developers of Hammer have done a really good job in storing the objects and not garbage collecting it. So our fuzzer basically takes the parser combinator object as an input and builds a parse tree from the parser combinator input, and it traverses the parse tree and generates all possible messages up to a certain depth. And we then fed these messages to our parser, and we looked for crashes. We didn't really find any because intuitively all these messages are valid messages that were generated from our parse tree. Okay, so the limitations of this fuzzing approach that we took was this, that we were not really doing much of mutation, and the second thing was that we were, the crashes that happened, we aren't really able to detect it automatically. We have to actually see through it. We have to actually open the log and see that it crashed. And this particular approach of fuzzing actually could have exposed logical flaws in our code, but then we didn't really detect any crashes on both of our parsers. Okay, so the lessons that we learned from this project was this, that parser combinator toolkits make it actually really easy to implement grammar in code, And the test that the implementation that we developed ran actually really well uh, on Raspberry Pis. Like it ran as good as existing implementations publicly available. Just that in some cases, depending on the language, it was slightly slower. And IoT protocols seem to have a lot of features and a lot of security features, and then half of them seem to not be enforced by a lot of implementations. And protocol specifications in plain text and in hundreds of pages is just really, really hard for developers to actually read through and understand. So we feel that it will be really good for developers if people who write these specifications, including us, should actually include the protocol state machine specifically and also the grammar for each of the receiving states. And so yeah, so the LangSec approach doesn't guarantee us success, but it does provide a very disciplined roadmap. And our next steps for this work is actually to use formal verification tools uh, and to build a smarter fuzzer than the preliminary fuzzer that we have built, and also diversify and build more parsers for more protocols. And that's about it. Thank you.
Let's take questions.
Yes.
You said overhead, is that just the time to parse the message, or is that overhead additional time over some type of reference implementation?
We did not really compute the overhead, it was the total time. Yeah, and we compared, in the same way, we actually compared the total time to other implementations. Yeah. Yeah.
Which, I didn't catch it. Which 3 backends did you say you used?
We didn't specifically use any backends.
Oh, okay. So you were
We just used the bindings and,
Oh, I'm sorry. Okay. I thought
Yeah.
you said you were using
No.
a couple different backends.
No.
Okay, so it was just Packrap.
yes.
Okay. That's the last.
So do you have any plans to upstream this to major open source projects for parts of these protocols, or do there not exist any standard?
So almost every major company has its own implementation for these protocols. So there is no really one place where we can actually push this technique. Yeah.
I was wondering whether you have thought of applying this to like protocols that are not built off of GCP, like for example Z-Wave or something.
So there has been work in that direction in the Power Grid actually, but not by this group specifically. But there has been work, and we would definitely love to look into that.
Z-Wave and 8.15.4 has interesting properties. The packet in packet was found in 8.15.4 as it for Z-Wave. It's using a two-channel scheme there, but ultimately the packet format, I believe, is the same. Fairly complex packets certainly could stand for some like that course.
Yes.
You use the combinators to generate a fuzzer of legal messages.
Yes.
Some programmatic way to tweak those combinators to get the slightly off on one kind of.
Yes, that is our next work. As I mentioned, we want to build some sort of a smart fuzzer. So the approach that I've been looking into is this: that I'm basically trying to feed this set of valid messages to a fuzzer like libfuzzer actually, that can actually take this set of messages as a corpus. So the corpus would basically, the libfuzzer would basically take it as a corpus and then mutate these messages and create off by one errors. Yes, we would use the combinators themselves to generate a corpus and feed, not to generate illegal messages. Yeah. Thank you.
Let's think it's